Alright, for this section we're going to take a look at factoring of polynomial expressions. So doing the opposite process of what we did for the last section when we multiplied, expanded out, and combined the like terms. So when we're talking about expanding and factoring, because they're opposite processes, we can look at the relationship between the two sides. We know how to expand out. We learned how to do that with the last section. If I'm doing a monomial and a polynomial, then I'm just going to multiply this coefficient by both parts that are in here. And I'm going to get 2x squared plus 10x. If I'm doing a binomial by a binomial to form a trinomial, well, then I can use the area model and get x squared, x, 3x, and 3, and I can combine those like terms. I can FOIL it, multiplying the first terms, the outside terms, the inside terms, and the last terms, or I can use the distributive property and say that it would be x times x plus 3 and 1 times x plus 3. No matter which way I do it, I'm still going to wind up with x squared plus 4x plus 3 when I combine those like terms. If I do the same process for the 2x plus 3 and x plus 4, well, if I FOIL this out, the 2x times x gives me 2x squared, 2x times 4 gives me 8x, 3 times x gives me 3x, and 3 times 4 gives me 12, and I just need to make sure I combine those like terms. 2x squared plus 11x plus 12. If I have two of the same binomials, but one has a plus and one has a minus, this is the only case where we have the difference of squares, where I'm going to multiply out a binomial times a binomial and get a binomial product. If I was to FOIL this out, I would get x squared plus 5x minus 5x minus 25. And remember that the positive 5x and negative 5x cancel each other out to leave me with x squared minus 25. In these examples, we have expanded a product of polynomials to form a sum or difference of monomials. In this unit, we're going to do the opposite process. If I'm doing the opposite process, I can remove a common factor, taking a look at both terms and saying, well, what's the same in them? Well, the 2 and the 10 are both divisible by 2, and the x squared and x both have at least one x in them, and when I divide that out, I'm left with x plus 5. The exact same as what I started with here. If that's true, then logically speaking, I could factor down the x squared plus 4x plus 3 into the x plus 1 and x plus 3 that we expanded out in the beginning. That means that this one would be the same as 2x plus 3 and x plus 4. And the last one would be x plus 5 and x minus 5. Now, how do we actually do this factoring? Well, let's start with looking at the greatest common factor. Now, you should have learned the common factors in that in grade 8 and grade 9. When we're doing it, we're going to break it down into what's called the prime factorization, which means that any number can be represented as just prime numbers multiplied together to create whatever that number is. To determine the greatest common factor, we need to know what is the same between the two. Well, they both have 3 2's, and they both have at least 1 3, which means that 3 2's and 1 3 is the same in both the prime factorizations. And when I multiply that back out, I get 24, which is the biggest number that both of these can be divided by. We can do the same process if I include variables, just thinking of a to the 3 as a times a times a, or a squared b as a times b. And then I'm just looking at what is the same. Well, they don't both have a 2, but they both have a 3. And they both have 2 a's, which means that it would be 3a and a is the same between them. 3 times a is 3a squareds. Now, when I'm actually doing the prime factorization, there's a couple of methods that you can use for prime factorization. The method that I typically use is called a factoring tree, where if I'm doing a factoring tree, I'm going to say that if I have 8 x squared y squareds, I'm going to split this up into 8, the x squared, and the y squared. Then I'm going to, for the coefficient of 8, try and divide it by the smallest prime numbers possible until I can't divide it by that anymore. And then I'm going to increase what the number is. So remembering the prime numbers would be 2, 3, 5, 7, 11, 13, so on and so forth. So I can divide this by 2, and I have a remainder of 4. I can divide 4 by 2, and I'm left with 2. And now I just have prime numbers. 2 times 2 times 2 is how I get 8. If I'm thinking of variables, remembering that I'm just splitting it up into x and x. The y can be split up into y and y. And the bottom of this tree is all of the different numbers and variables, prime numbers and variables, that are being multiplied together to make this whole. Which means that 8 x squared y squared is actually the same as 2 times 2 times 2 times x times y times y. Now you can see that the times symbol and the x's can get confusing. So typically what we do is we use what's called an interpunct, or a multiplication dot. And you'll see this more and more in the stuff that we're doing, where we just use this little dot to say that they're being multiplied together so it doesn't get confused with the variable x. If I do the same thing with the 20xy cubed, 20 gets its own category, x gets its own, and y cubed gets its own. Well, the 20 is going to split up into 2 and 10, and 2 and 5, and because 5 is a prime number, I can't divide it out any further. The x is already done, it's just going to stay as x, and the y cubed is actually just 3 y's. And there's all the different things that are being multiplied together to make 20xy cubed. If I'm determining the greatest common factor, remember, I'm looking for what is the same. They both have 2 2's, they both have an x, and they both have 2 y's, which means the greatest common factor is going to be 2 times 2 times x times y times y. And when I multiply that back out again, I get 4xy squared. The greatest common factor of 2 simple monomials can be determined by inspection, taking the greatest common factor of any numerical coefficient and multiplying by each common variable to the lowest exponent. So when I take a look at these two, what that means is I can just look at 10 and 15, and it should be simple enough to know that those are both divisible by 5. That's the biggest number. Now, because this one has P3 and this one has P2, I need to take the one with the smaller exponent, which is the P squared. If I look at Q and Q squared, then Q to the 1 has a lower exponent. So I'm taking 5 can be divided out of the 10 and 15. P squared is the smallest number of P's, and Q is the smallest number of Q's, and expand that out to get 5p squared Q. If every term is going to be negative, then usually we pull out a negative as a common factor. If one of the terms is not negative, then depending on the situation, we may or may not pull it out, but typically we don't unless they're all negative. So when I'm taking a look at these examples, well, if I look at example A, then for 12 and 15, the biggest number they can both be divided by is 3. This one has 1a, this one has 2a's, so I can only take out 1a, and this one has 1b, and this has 3 b's, so I can only take out 1b. For example B, if I have 18 and 24, well, they're both divisible by 2, by 3, and by 6. Well, obviously, 6 is going to be the biggest number I can divide both those by. Then I have x to the 4 and x to the 3, so I can only take away 3 x's from both. And I have y to the 2 and y to the 5. I can only take away 2 y's. For example C, the first one does not have a coefficient, so there is no numerical coefficient that I can pull out. I can just look at the variables. Well, this has 3a's and this has 1a, so I can only take out 1a. This one has 1b and this one has no b's, so I can't take out any b's. And this one has 2 c's, and the second one has 7 c's. AC squared is going to be the common factor. And for the last one, if I have negative 40, negative 20, and negative 10, it's divisible by 2, 5, and 10. So I'm going to pull out a 10. Because they're all negative, I'm going to make it negative 10. And then I can take out an a squared because they all have at least 2 a's, and I can take out a b because they all have at least 1 b in them.